And this is one of the good things about this notation. Everything after here is a multiple of 0 to the power of 4. 0 to the power of 4 is 0, so everything after this is a multiple of 0. Multiple of 0. Everything after here is a multiple of 0. Everything after here is 0. That's 0. 0 cubed is 0. That's gone. That's gone. That's gone. Now sine of 0 itself is actually equal to 0. So we found out that a0 is actually equal to 0. So let's write that down. We have that a0, the very first term, is equal to 0. Now this sounds disastrous, like we've infinitely many problems because we do a1, a2, a3, a4. Now if we want, we can just say, oh, we're just going to take the first few terms. And I think for our purposes, we actually only need the first 4 terms, but we'll show you that there's actually a pattern to this. So now differentiate both functions, differentiate this and differentiate this. So if you differentiate sine of x, you get cos of x. Differentiate a constant a0, you get 0, plus fix the constant a1, and the derivative of x with respect to x is 1, plus fix the constant a2, and the derivative of x squared is 2x, plus fix the constant a3, times the derivative of x cubed is 3x squared. And here's the good bit. If you differentiate things that are multiples of x to the 4, they are multiples of x to the 3. Because if it's x4 times something, you have a product rule. The first thing is, so you do say x to the 4 times something. Product rule, you have x to the 4 times the derivative. And that's a multiple of x cubed because it's x times x cubed times something. And then plus the derivative of x to the 4, or multiple of x to the 4. If you think about it, it has to be a multiple of x cubed. So if you differentiate order x to the 4 terms, you get order x to the cube terms. Here you can see a bit of this notation being useful. And what we're going to do is we're going to plug in x equal to 0 into both sides. Now I'm going to go a little bit quicker here than the previous. So if you put x equal to 0 in here, you get it's a multiple of 0, that's gone. Put in x equal to 0 here, multiple of 0, that's gone. And everything here is a multiple of 0 cubed, is a multiple of 0. So everything after that is 0. So all you're left with is a1 times 1, which is just a1, is equal to cos of 0, which is 1. So we found very, very slowly a1 is equal to 1. Repeat the trick, differentiate both sides of this. So you get minus sine x, minus sine being the derivative of cos. The derivative of a1 times 1 is just equal to 0. Now I'm going to fix the a2 times 2, and the derivative of x is 1, plus I'm going to fix the a3, I'm going to fix the 3, and the derivative of x squared is 2x. And when you differentiate terms of the order of x cubed, you get terms of the order of x squared. And if you substitute in x equal to 0 into both of these, gone. These are multiples of 0 squared, that's gone. As it happens, minus sine of 0 is gone. And you end up with 2a2 is equal to 0, so a2 is equal to 0 as well. Now really what I'm actually interested in is not that it was 0 necessarily, really what I'm actually interested in, and similarly with this, we'll probably just go back over these in a second. There's a pattern to this. So the pattern is as follows. a0, remember we're talking about sine of x in particular, but in general we're talking about f of x. This is equal to the value of the function at 0. The next thing, if you look at it and examine it, this is actually equal to the derivative evaluated at 0. This is the second derivative evaluated at 0, and to find a2 you'd have to divide by 2. So this is the second derivative divided by 2. This is going to be, if you do repeat the trick, you're going to have 3 by 2 by 1, which is 3 factorial. That's what factorial means. And over here you'll have the third derivative. So you'll end up with, if you carry through the analysis, a3 is the third derivative at 0 divided by 3 factorial. And with a bit of thought, you can see that the coefficients are going to look like this. A to the not a to the power of n. So the nth term here is the nth derivative evaluated at 0 times n factorial. And you might say, Asher, what good is that? Well, the thing is, for stuff like sine and cos and exponential, and I think even log of 1 plus x, there is a pattern to the derivatives at 0. So for example, for sine of x, the pattern is 0, 1, 0, minus 1, 0, 1, 0, minus 1, etc. And for, say, the exponential function, all the derivatives are the same, and at 0 they're all equal to 1. So actually it's more useful than it looks. Okay. And we will go, well, let's see what we're looking at. I don't know how far we'll get here. So this is the Maclaurin series formula. This is putting it all together. Remember, we had saying that the function was a0, a1, x plus a2, x squared plus a3, x cubed. And then this is in sigma notation. This is ak, x to the k. And we found that a0 is the value of the function at 0. We found that a1 was this, a2 is this, a3 is this. In particular, what you can do is truncate. So truncating is where you cut off a lot of these. You can just take the first few terms. And usually this is going to be very good because with Maclaurin series, you're near x equal to 0. And past this, you're talking about terms. I can actually write something down here. All the terms in here are all multiples of x to the 4. In a particular way, I think you can show with a bit of work that although there's loads of them, like there's x to the 4, x to the 5, there's infinitely many. I think it is possible sometimes to show that they're all less than or equal to a multiple of x to the 4. But what I'm interested in saying here is that if x is close to 0, I'm saying that x is small. And if x is small, x to the power of 4 is, and when I say small, I mean less than 1, or less than 1 in absolute value. So if x is small, x to the power of 4 is small as well. And so what you have is that the terms after a while get really, really small. They're all multiple. I say take point 1. Point 1 to the power of 4 is 0.0001. So they're all a multiple of that tiny number. So they're all tiny, so you kind of forget about them. So this is a reasonably good approximation. If you want to be a bit more careful, you can add on another one or two. Okay. So, now the thing about this Maclaurin series is that not all functions are nice near x equal to 0. For example, log of x. If I asked you for the log of 0, you're in trouble. Have a think about it, ask the calculator. This example shows that not all functions are analytic. Analytic means a function is analytic if it is equal to a power series. So not all of them are, and log of x is not equal to a power series near 0. It's not even defined there. However, suppose that a function is analytic near a different point. It turns out that a similar analysis gives you, if you think that a function f of x is equal to, how do I write this now? Say a0 plus a1 times x minus a plus a2 times x minus a squared plus, and now I'm going to use my order notation. Everything after this is a multiple of x minus a. They're all multiples of x minus a to the 3. And remember, x minus a to the power of, say, 7 is x minus a to the power of 4 times x minus a to the power of 3. It is a multiple of that. Okay, an identical analysis gives you this formula. This is basically the same thing, except if what you have, if you're not interested at x equals 0, but maybe near a different point. Okay, and the Maclaurin series is the same thing as the Taylor series, except you're like, so for argument's sake, if you're working with log of x, you wouldn't find the Maclaurin series, you'd use the Taylor series, and instead of close to 0, you go close to 1, because that's the point that you know about. Okay. Right, now we have the tools with these power series and the language of order to help us analyze Euler's method. Hopefully we don't run out of time. So the numerical solution of ODEs involves two types of errors. Truncation. So this is the technique. The Euler method is not perfect. It's only an approximation. So you're getting errors. We've seen this earlier on. The other thing is round-off errors. And that's if you use any rounding. And a computer will use rounding as well. Now we can control the first, but the second is just something we have to be very, very wary of. We can estimate the truncation error. So what I'm saying here is, using Euler's method, we can find out how bad it is using Taylor's series. And some of this, really, it's mostly the conclusion I'm interested in, so I might speed past things, because as I said, it's just the conclusion I'm really interested in. So, we've got a differential equation. Most differential equations that you write down, the solutions are nice in the sense that they're analytic. So the true solution, the exact solution, can be written as a power series. It'll be analytic near the starting point. So instead of putting a, I put in x0, and instead of f's, I have y's. Okay. And what you can show is that, and it's kind of up here. Where will I write it? So see this Rn. This is, everything after this is a multiple of x minus x0 to the power of n plus 1. Now the concern is that there are infinitely many of them, and maybe it gets really, really big. But what you can show with heavier techniques than what we're going to look at is that in fact, this infinitely many terms that are all multiples of x minus x0 to the power of n plus 1, in fact add up to something that is order x minus x0 to the power of n plus 1. That means a multiple of this. And in fact, all these infinitely many terms add up to, in fact, this thing. So what is that? So I'm saying it's a multiple of this. This is the multiple. Now what this thing is here is the n plus first derivative at some point in between x0 and x. We don't really want to have to go into that. All I want to say is that it's all these terms that are all a multiple of this can be all expressed as a single term that is a multiple of this. Right. If you are looking at thinking now of Euler's method, where you're starting at x0 and you're going to x0 plus h, the x we're interested in is x0 plus h, and so what we're looking at is x1 minus x0. So this is the difference between where you're going to and where you started. This is actually equal to h. So if you're using Euler's method, or indeed any, this is just true in general, that, and I think this is missing one thing, this should be x1. The true solution looks like this. So at x1, at the next point you're interested in, the exact solution is equal to this. Now the problem is this is a finite thing, but this is a theoretical thing. You're not going to be able to find it in general anyway. Right. Now, with Euler's method, what we are doing is we're actually only going up to the first derivative. So if I just write something very similar to what was on the previous page, the exact solution is equal to y of x0, that's the previous x value, I'm going to write step size here, times the slope at the previous point, plus the remainder term. And if you look at on the previous page, and this is the really important part, okay, so the really important thing is that R1, like here, so look, Rn is order h power of n plus 1. This is the whole thing. R1 is equal to some multiple, don't care what it is, of h squared. So what we have here, the exact solution, this is the Euler method, plus R1 and the error, sorry, let's get this right. So the true thing is the approximation plus the error. So the error is a multiple of the step size squared. This is the crucial thing. So what we have is that so the true value, the exact value, y of x1, is equal to the approximation plus R1. Well, actually, in general, the true value is the approximation plus the error. And in this case, the error is R1. So this is the approximation, this is the true value. So R1 is the error. And the error, R1, is order h squared. Now, you might be a bit lost at this point, but this is very, very good. This is very, very important. What this says, that if you're going in, now this is just for one step, the very first step, the error is h squared. And ask yourself, slow down, what happens if you halve the step size? Well, because the error is order h squared, halving it will actually quarter the error. So this local error, if you halve the step size, you reduce the error by a factor of 4. If you reduce the step size by a factor of 10, so instead of going in steps of 0.1, you go in steps of 0.01, the first error, if this is 0.1, and you reduce by a factor of 10, it'll be reduced by a factor of 100. This is good. Now we'll see exam questions of this, but this is the big theory here. Now I will skip this bit. This is kind of saying, you can read this yourself, but it's basically saying, oh, can I actually find the actual number? And here it does that. Okay, you can kind of compare the two, but I'm not too interested in that. It isn't typical that we can find the point where, it's really not important. What is important is that, so this is, if you are using Euler's method, we know that the maximum error over the first step is, let's see, so the error is certainly less than, and this is kind of written up here, so we'll do it. So it's certainly less than the maximum second derivative, this is just more or less taken from above, divided by 2 times h squared. Now really, I am actually not so interested in the second derivative max, because I don't control that. If I'm given a problem, I can't control that. The thing that I can control is the step size. And so this is a multiple of the step size squared. So it's order h squared. Now this is the error over a single step. And the error over a single step we're going to eventually call the local error. So this will be epsilon L. But it's just talk, and I really don't care about this, but in this particular example, it's not that you want to find the exact thing that gives you the exact error. Just say, oh, it's less than the maximum, and then even then you can say, oh, I'll look at the maximum second derivative. But even then, I actually don't care about that. Just cover here. So maybe, okay, to maximize the second derivative, it's not difficult. This thing is a minus x squared. And so the max occurs where the derivative is 0. So you just differentiate the second derivative. I don't really want to write dy dx, but so I want the derivative of the second derivative, the third derivative, which is minus 12x plus 24. I want this to equal 0 and I think I end up with x is equal to 2. So what I could do is I could put that 2 into that. Oh, what do you get? I'm not sure. 48,